So this is lecture number 4 in this series on electrical machines. So far we have studied a simple rotating loop, how a simple rotating loop experiences torque when a current is flowing through it, supplied to an external DC voltage source, as well as how a voltage is induced in this simple rotating loop when placed in a magnetic field and rotated by means of an external mechanical energy source. So it emulates the behavior of a DC machine, but it does not sufficiently tell us about the actual behavior of a DC machine. An actual DC machine will be somewhat more complex than a simple rotating loop placed in a magnetic field. There are a number of parameters that need to be taken into consideration. We need to study it thoroughly. So first up, we'll be starting with the construction of a DC machine. We'll be looking at how a DC machine actually looks like. So this here shows us this is a representation of an actual construction of a DC machine. Now whether this is acting as a DC generator or a DC motor, the construction will look similar, as well as we'll have different types of DC machines, as I have discussed earlier, also separately excited, shunts, series. So overall the construction is almost similar with slight differences that we'll be seeing when we start with the types of DC machines. So here, as you can see, there are a number of components. The important components here include a frame, yoke, we have the frame, we have the yoke, we have the field poles, so poles will actually consist of pole faces and pole shoes. We have the armature, we have the commutator, and brushes. Fine. So you look at this picture. This is the frame representing the outer cylindrical surface covering the entire DC machine. We have the yoke that's actually internal to this frame. Then we have the field poles and the field cores. So field poles and field cores will something look like this. Fine. So this will be actually the I can slightly represent a 4-pole DC machine like this. This here actually represents the yoke. These are the poles. Fine. So poles consist of pole faces and pole shoes, and in between the pole face and pole shoes lies the armature. So this is, you have been shown the armature. These are the armature windings. Fine. Then you have the commutator and brush segments that actually help us convert the AC voltage generated in the armature or induced in the armature to produce a DC output voltage. So this is about the constructional, the overview of the different parts of the DC machine. We'll be studying all of them in detail, and apart from that, you'll be having some other parts associated with this. You will have the nameplate where actually the ratings of the DC machine will be given. You'll be having end bells here. You'll be having fans, you'll be having fan for cooling purposes of the windings. You can even have in a larger machines this you'll see a groove at the top. This is the shaft of the rotor. So these are about the different parts of a DC machine. So I've downloaded this picture from the net. You can see in this more clearly the different components of your DC machine. Right. So as I said to you previously also, the main components of a DC machine are the stator and the rotor. That's the stator is the stationary part and the rotor is the rotating part of the circuitry. And most importantly, we have the field windings on the stator in case of a DC machine, and we have the armature on the rotor in case of a DC machine. So apart from field windings being stationary, you also have the yoke that's actually stationary and the yoke is not moving. Uh, so uh, Talking first about the yoke, the outermost structure of the DC machine is a frame that actually will enclose all the will actually enclose the DC machine as a whole and support it from bad weather conditions and extra from the environment. It will not have any magnetic or any electrical interference with the machine itself. Talking about the yoke, of a DC machine, it actually supports the poles. The poles are actually adjusted on the yokes, and this provides the path for magnetic flux. Yoke, it supports the poles. And allows the windings to be wound on the poles, fine, and it will also provide the path for magnetic flux. So actually the magnetic flux will be moving through the yoke. Through this part, the magnetic flux will be moving from the yoke. The magnetic flux will not be directly will not as such be moving in the frame of the electrical machine. Fine. So this is about yoke. It supports the poles and allows the winding of the field windings to be wound on the poles. So poles, as you can see, they are again physical structures that allow the field windings. So these are referred to as poles as a whole. These are your poles. They allow the windings to be wound on it, and so that they can be distributed in space uniformly across this across the circumference of the armature. So poles now consist of two parts: the pole shoes and the pole faces. So just like the yoke, poles also provide path for the magnetic flux. Fine. So this part here, it is known as pole shoes, and this part on which the windings are actually wound are known as the pole faces. So pole faces basically allow the windings to be wound, and allow these windings are actually the field windings. So the field windings will be connected to an external DC voltage source, so that current is established through these field windings, and once the current flows through these field windings, they will produce the electromagnetic field. So we actually have electromagnets instead of having normal magnets now in larger DC machines, like in case of small DC machines that you may have seen in case of small toys or cars, right? You have seen magnets being placed in the DC machine. It's a DC motor there also. You see magnets there placed, but in case of larger DC machines, of high rating DC machines, we do not use magnets, we use electromagnets. So for that we use actually field windings that are excited by an external DC voltage source. So once a current is established in the field windings, and as I told you, how we wind these, we make sure that one set of winding is clockwise and another set of winding is anti-clockwise. So you can see on one pole face here, this is showing that the windings are in this direction. They have been wound in this direction. The windings are in this direction, that is actually anti-clockwise. If you see on this pole face, the windings are coming out from here and going in from here. As the windings are coming let me show this again. The windings are, it's coming here, it's going into this, and then moving out from here like this. Fine. So this is actually a clockwise winding, whereas here in this case it is coming in from here, coming out from here, and then going back in to this and coming out from the back. Fine. So this is actually an anti-clockwise winding. So here you can see clockwise, the windings have been wound clockwise, while as on this pole face the windings have been wound counterclockwise. Again, in this case, if you will see, it should be clockwise, and on this pole face it should be counterclockwise. Since the direction of current will be clockwise in one pole, anti-clockwise in another pole, so one of them will act as north, another one will act as south, north and south. So they will act just like the poles of a magnet. So this is how the field windings have been wound over the pole faces. Now you can see the construction of the pole shoes. The pole shoes basically spread over the armature. They have been made sure that they spread over the armature. Now why we spread this pole shoe over the armature? So that minimum amount of air magnetic flux actually is leaked in this DC machine. Fine. We want to make a uniform one. We want to make sure that this gap between the armature, or you can say the rotor, and the pole is one. It is uniform. Fine. So the pole shoes make sure one, uniform air gap, between the pole and the rotor. So across the circumference of the rotor, we make sure that the air gap between the poles and the rotor is uniform, one, and two, it also makes sure that leakage flux is minimum. as it covers almost the entire circumference of the rotor. Most of the flux will be associated, that actually is generated from the poles, will be associated with the rotor, and minimum amount of it will get leaked into the air. So this is the construction of a pole. It consists of pole faces and pole shoes. The pole faces allow winding. The pole faces allow winding of field circuit. So the field circuit that we'll be talking next, field windings. As I said to you, field windings are basically wound over. They are wound over the pole face in a manner to produce north and south alternately. So on one set of pole you will be producing a north because the windings will be clockwise, and on another set of pole face the windings will be counterclockwise, so it will be producing a south. So this is how you produce a field winding. They actually are responsible for production of magnetic field in this electrical machine. That's the main important role, the production of the magnetic field. Fine. Now you can have different number of poles. You can have a 2-pole machine, you can have a 4-pole machine, a 6-pole machine, an 8-pole machine. Fine. So depending upon the speed and other ratings, voltage ratings, will be deciding the number of poles for a electrical machine. So we'll be seeing the equation how speed and voltage are related with the magnetic poles later, and we'll see accordingly how we choose the number of poles for a system. Following the field windings, you have the armature, or you can say the armature windings. You have actually the rotor. So if we look at the rotor, it's a circular structure with slots and teeth. Fine. So these are the slots, and these are the teeth of the DC machine. And the windings, these dots here actually represent the windings that have been, they are actually conductor bars. We actually place conductor bars in these slots, and then we connect each and every conductor bar so as to complete the circuitry of the armature windings. So these conductor bars placed in the slots of the armature are connected with each other. So you can have this conductor connected connected here, connected here. So each and every conductor will be connected in a different manner actually with the next conductor, so as to form a complete circuit. So armature, it's a circular structure and it consists of slots and teeth. Conductors are placed in slots and connected with each other to complete the circuitry. So what is the role of this armature winding? If this is a DC motor, you will be supplying, you will be actually this armature windings will be connected to the armature terminals through this commutator and brushes outside, and the armature windings will actually always be carrying AC, whether it's a DC motor or a DC generator. The windings always will carrying AC current. It will not be carrying DC current. So in case of a motor, it is the armature windings that carries the current when placed in the magnetic field. In case it's a DC generator, it is the armature in which the voltage is induced when placed in the magnetic field and rotated uh, by means of any mechanical energy source. So you have armature windings, you have armature conductors. Regarding this, I will be shortly telling you how these windings of the armature are wound. Number 5, you have commutator and you have brushes. Fine. So commutator and brush segments, they are actually meant for converting and collecting. So commutators basically convert the AC voltage that's actually present in the generated in the AC in the armature windings into DC, and the brushes are responsible for collection of those windings. So typically a commutator is made up of copper bars and its important job is that of commutation, that is the process of AC to DC conversion. Fine. Brushes, they are made up of carbon or graphite and they will be responsible for collection of current. So commutator and brush segments, they actually work together for conversion of AC to DC, or if it is a DC motor, then they will actually feed the DC, will be fed with DC voltage and convert it into AC current in the to be that actually will flow through the armature windings. So you can see these are the commutators. So commutators are actually number of slots, and you can see you'll be actually numbering these slots later on, 1 2 3 so on. And the brushes, they are actually these black brushes, they will be fixed. The commutator will be rotating along with the commutator will be rotating along with the armature, but the brushes, they are fixed, they are stationary, they do not move, and they are responsible for collection of current. Now since the brushes are actually moving over the commutator, that's why brushes are made up of carbon or graphite to reduce sparking and to make minimum wear and tear with the brushes. We'll be studying the process of commutation of a DC machine in detail. We'll be seeing what are the issues associated with commutation. This we'll be studying in detail. Now going back to the construction of armature windings. These are actually the manners in which the windings, in which we wind the armature windings. There are two types of windings we carry out in a DC machine. One is known as the lap winding, and second one is known as the wave winding. In case of lap winding, what we do is, I'll show this through an image. So these are your lap windings. This is your lap winding and this is wave winding. So what is the difference in these two? This is your armature. The slots have been numbered 1 2 3 4 so on. There are conductors, and at this moment you can say that These conductors have been numbered as, again, there are two conductors in each slot for the time being, and let's have that. And then you have commutator segments. They have been numbered as A, B, C, D, E. Fine. In both cases, you have one. You have in both cases, in the lab winding as well as in the wave winding, you have these two. You have the numbered slots, and you have the numbered, alphabetically numbered commutator segments. Now, in case of lab winding, you can see this is a coil that's starting from slot number 1 and connected to slot number A, while as in this case, and in the slot number 2, the upper wind conductor is starting from slot number 2 and connected to slot commutator segment B. In case of slot number 3, the upper conductor is connected to commutator segment C. 4 is connected to D. So it is actually progressing in this fashion. Why? While as in this wave winding, whereas in case of a wave winding, you have first slot, we have shown here only one conductor. So the conductor of the slot is connected to commutator segment A, but the conductor of next slot is connected to commutator segment D. It is not connected to commutator segment B. Some another conductor is actually connected to commutator segment B. So when we lay this flat, if I lay this flat, I have, these are my commutator segments, 1, 2, 3, 4, 5. These are commutators, 1, 2, 3, 4, 5, 6, and I have coils. So this is a coil of an armature winding. So you have number of slots of the armature. As in this case, you are seeing 8 slots of armature. In this case, in this particular machine, you have 8 slots of armature. You have number of conductors, fine, but these conductors are connected in a fashion such that starting end of one coil and the finishing end of another coil are connected to side by side commutator segments, and another coil will actually start from this commutator segment in this case and end up at the next commutator segment. Next coil will start from here. So electrically all of these coils are connected, so they will actually form the same winding. Fine. So ultimately you'll get one terminal here and one terminal here if it's a two-pole machine. So there will actually be only two terminals in any DC machine from which you can supply or receive the DC voltage. These coils are connected in this fashion. If they are connected in this fashion, where you have the starting end of one coil connected to commutator segment 1 and its ending connected to commutator segment 2, and from there only you have another coil that starts. So these are now coils that I will number here. So there is one coil, this is your second coil, this is your third coil. So each coil now has two turns. This is referred to as a turn here. So one coil side, you can also call this as coil side. So one coil side is connected to commutator segment 1, another coil side is connected to commutator segment 2, and from the commutator segment 2 only the coil number 2's starts and it ends at commutator segment number 3. From commutator segment number 3, coil number 3 starts and it ends up at commutator segment 4. From commutator segment 4, coil number 4 starts and ends up at commutator segment 5. So these coils actually lap over each other. That's why it's known as a lap winding. While as in this case, what happens is, if you have one coil side connected to commutator segment 1, another coil side will be connected to any other commutator segment, but not the next. It will not be 2, it can be 3, 4, 5, 6. It can be, I will rub this off. Fine. You have this will end up at commutator segment 5. So from commutator segment 5, the next coil will start, and it will also end up somewhere at, say for example, at 11. So coil number 3 will start from 11 and finish at, say for example, commutator segment 17. It may start from 17 and end up back at 1. Fine. So this is how windings can be arranged. Either it will be in this fashion, where you have each coil side connected to the next alternate commutator segment, or in the second case, you have coil sides connected in such a fashion that they end up at some other commutator segment whose information we actually do not have right now, but we'll be actually looking at where it will end up. We'll be looking at different equations associated with this. But what happens therefore is that in such a case, the machine no longer has lap windings. These windings are more like a wave, and that's why it's known as a wave winding. In the next session, we'll study these two windings, the lap windings and the wave windings, in detail, because based upon the construction of lap winding and wave windings, we'll be able to deduce the EMF equation of a DC motor or a DC generator. These windings are very important, and we'll be studying them in detail. It will take us from here 1 or 2 to 3 lectures rather, to wrap up this lap winding and wave winding. So that's all for today. This is about the construction of a DC machine. We have studied different parts that are associated in a DC machine, and most importantly, we have to study the winding type of armature, whether they are wound as a lap winding or they are wound as a wave winding.